In this video, we will be going over the C2MATLAB translation using neural machine translation. Previously, we discussed MATLAB to C translation using the same approach. Here, I'll go over how datasets are prepared and used to train TensorFlow's neural network, as well as the source code of the translator itself. To review, TensorFlow's translator is a sequence-to-sequence neural network. The encoder takes a source sentence converted into a sequence of numbers, and the decoder predicts the most likely translation or target sequence for each part of the source sequence, while using an attention mechanism to influence the prediction based on the content or context of the source sequence. Now I will be showing the demo which walks through the training process and demonstrates the translation functionality of the tool. To use a translator, you must first train it on actual examples of source-to-target language translation. In this dataset, the source language is C code on the right, and our target language is MATLAB on the left. Each line in C corresponds to a line in MATLAB. To prepare the data to be used in the translator, we have to perform several pre-processing steps on the text. So, for pre-processing, we use three scripts: tox, mtokenizer, and concat. Both of these files handle the tokenization of the MATLAB and C code. Tokenization, in this case, parses the code and separates the text into tokens or symbols with meaning. So variables, variable values, operations, and so on are separated for ease of manipulation. And, as you can see here, non-alphanumeric symbols are replaced with temporary tags. So the left round bracket has its own tag, and the variable name record is replaced with a generic tag. And a similar operation is done for the MATLAB code. We use tags to replace variable values and numbers, generally tokens that vary from program to program. This is important because this data is also used by the translator to build the vocabulary of the source and target languages. And without replacing the variable and number values with generic tags, the translator will be unable to translate code with variable names or numbers that aren't found in the training data. Then, after both C and MATLAB are processed, we concatenate them together into a single file. On each line, the target MATLAB code is on the left and the source language, C, is on the right. This file is used to train the translator. So, the main output of the scripts that we will be using is the concatenated file to train the neural network, as well as a pickle file that serializes a dictionary of all the generic variables and number values that the tokenizer replaced with generic tags. Here, we will provide a quick overview of the neural machine translator. Here, we specify the training data that we're using to train the neural network. And here, we specify our checkpoint directory. A checkpoint directory is created from the neural network during translation. In case training is interrupted, these checkpoints are used so that the program can resume where it left off the next time it runs. Here's one example of the checkpoint directory. This is also used as our model. Here's a variable that indicates whether or not we should train the neural network. In our case, the training variable is set to 0 because we've trained this translator beforehand with the training data shown before. This is a function which converts Unicode files to ASCII. And here's a function that shows the pre-processing of the sentence. Now, this function is mostly used for natural languages such as English to Spanish. For c2matlab, we have our own tokenizers. But each line, each source sequence and target sequence needs a start and end tag so that the translator knows to start and stop translating a sentence. These are more functions that help prepare the dataset. These are the values which indicate the structure of the neural network. For example, the embedding dimensions are used to initialize the embedding layers of the encoder and decoder. And here the neural network separates the dataset into batches to be trained. This is the encoding layer. And here the embedding dimensions are used to initialize the embedding layer of the encoder. This is the Badenow attention object, which is used in the decoder to help predict the translation using context from the source sentence. And the code shown here is based off the Badenow equation. Now, the score used to help calculate the context vector varies depending on the approach. This is the Badenow approach, but there are other ways to calculate the score and other equations. And this is the decoder, which also uses the embedding layer with the given embedding dimensions. And here it initializes the attention mechanism. And the attention mechanism calculates the context vector and attention weights under this function. The loss function is used to calculate the prediction error during training to help optimize model accuracy. And the train step is called for each batch of data which is trained and returns the batch loss, which is used to calculate the total loss during training. and the evaluate function is used to actually translate a sentence after the neural network is trained. The main difference between training and translation is that during translation, the decoder input only receives the start token of the source sequence. During training, the decoder will receive the correct target word for the source word in the sequence. And the translate function is the starting point to translate a source sentence after the neural network is trained. Here's the actual training of the neural network. The encoder is initialized, the attention and the decoder is also initialized. And here we train the neural network for 20 iterations and for a batch size of 32. And that is the source code of the neural machine translator. Now we will demonstrate how to use the program to translate a segment of C into MATLAB code. Here is the input text, as well as its expected translation. The function eediv is meant to emulate the element-by-element division operation in MATLAB. Now let's just have the C code by itself. First, the input is tokenized and a dictionary of variables is created. This is the serialized dictionary, and this is the tokenized input file. Here the special symbols have been replaced, as well as variable names and number values. Then, we run the translator while specifying the input and output files. Here, the input file is the tokenized text, and the output file is just going to be called demo output. Here is the resulting translation of the C code from the neural machine translator. However, post-processing steps are needed to make this translation more readable. So we will use our fourth script, the reverse tokenizer. And this is going to replace all the generic variable and number tags as well as the tagged symbols using the serialized dictionary that was generated during tokenization. Now let's just have the full translation by itself. Now, we are going to call the script while specifying the translated file, demo output, as well as the serialized dictionary that was created. Now we're going to call the reverse tokenizer script using the output and the serialized dictionary that we generated. And this file is the final translation. And it matches our expected translation from earlier. This has been a demonstration of TensorFlow's neural machine translator, as well as a demo of C2matlab translation.